Hi everyone, Architecture and Operating Systems. We are in week 3, and in this week we are going to learn more about digital gates. So Boolean logic, not, and or. What are they? So guys, so far we discussed binary numbers, how to add them, how to subtract them, and divide and multiplication. Also we learned about the negative numbers. So when we're talking about the, for example, making negative numbers, and I said that, okay, for making one's complement of this simple number, what you need to do, only flip the bits, which is 1, 0, 0, 1. So that's perfect, and I showed you how we can use this method to subtract two numbers. But the question, how computer does that? Okay, I told you in the week 1 that when we have high voltage, we say it represents as 1, and if we have low voltage, we have 0. 1 and 0 are the numbers that we use to show those signals, and everything in computer works based on is binary 1 and 0. But how we can flip that bits, for example, 0 to 1, 1 to 0. So we use different gates, not only this, for example, for adding, how come 1 plus 0 is 1? How we can do that? We use digital gates, some hardware components that we will discuss them later in more details, but what is important to know is how computer does that. So we have several gates that we study them one by one. The first one is not or inverter. Not or inverter gate. We show this physical gate by a triangle and this, as you see. What it does, if you have an input, here we call it input, and here we call it output. Input can be A, output can be X. If you have input 1, it inverts that, make it 0. If you have input 0, it flips that and makes it 1. So the output is the invert or opposite of whatever you have as A. So if this is your output, it's equal with A not, this is the sign, or A bar. These two signs show the not. So this is called not gate, because that's a gate and it inverts that. So as I told you guys, that if I have this lovely gate here, if I have 1, I get 0. If I have 0, I will get 1. But it's good to show that in a table. So we can have a table. A is the input, X is the output. So we can see all the permutations of the input and output of this gate or circuit. If we have 1, it inverts that. If we have 0, it inverts that to 1. What is that table called? This table called truth table. It means that we can understand what happens in this gate by this truth table. So, for example, just show the application of this. Imagine that I have this number. In one's complement, I know that I've got to flip the bits. There you go. In reality, what happens? What you need to do, just put a NOT gate in front of that. So look guys, input is 0 is output. Input is 1, the output is, input is 1, output is 0. 1, 0, 0, 1. So as you see, we discuss one's complement, but in the hardware, what happens? If we use this physical thing, if the voltage is low, it makes it high. Or if we have off, we have on them. If we have 0, we have 1. So NOT gate is the first one that we discussed, and it inverts the values. So let's go to the next one. The next gate that we want to discuss is called AND gate. So look guys, in multiplication, I told you if you have 0, multiply by 1, you get 0. 1 times 0, 0. 1, 0 times 0 times 0, 0. And 1 times 1 is 1. Okay, how we can show that? If we need to have a gate that when one of them is 1, one of them is 0, the output is 0. Look guys, if one of them is 0, the output is 0. But when both of them is 1, we get 1. What gate do we use? We have a gate, we call it AND. It's an AND logic actually. So we can have input A, we can have input B, and we have output as X. What does it do? It's an AND logic, guys. It means that both of them should be 1 to get output 1. It means that here, if A is, I'll show here, if A is 1, B is 0, the output is 0. If A is 0, B is 1, output is 0. If A is 0, B is 0, the output is 0. And if A is 1, B is 1, the output is 1. This is called AND gate. As you see, when both of them are high or 1, both the inputs, we get 1. How we show that? X is equal A, B. We show this AND gate with 3 notations. One of them is dot, similar to multiplication. Or A hat B, this sign. Or if you don't put anything like this, anything between them, like that, we call it AND gate. Nothing there, hat or dot, all of them show the AND gate. So, truth table, there you go. We need to have truth table for this gate. A and B are the input and X is the output. You need to have all the permutations here. So when A is 0, B is 0. A is 0, B is 1. A is 1, B is 0, 1 and 1. What are the outputs? AND gate is on, or the output is 1 when only both of them are 1. The rest is when you have 1, 0, we get 0. Let me delete that. There you go. This is our AND gate. So another basic gate that we have, we have another one called, let me make it a bit, yeah. We have another gate which is called OR gate. What is OR gate? OR gate we use, not always, but when one of the inputs are 1, we get 1. For example, I have 1 plus 0, not always correct, guys, but something similar to this. 1 plus 0 is 1. So if one of them is 1, we get 1. 0 plus 1, 1. When one of them is 1, we get 1. 0 plus 0, 0. None of them is 1. 1 plus 1 is 1, 0 carry 1. But for these 3, I can actually use this concept and say that, oh, when one of them is 1, we get 1. OR gate, we show it like this. I have 2 inputs, A and B, and I have output. So how it is? Look, guys, in our OR gate, when one of them is 1, the output is 1. Oops. When A is 0, B is 1, this is 1. Both of them are 1. At least one of the inputs for the OR gate, at least one input, I write it here. At least one input should be 1. Then the output is 1. At least one of them, look, at least one of them. When both of them, we get 1. I told you that's similar to addition, not 100% right. Not 100%, actually, it's exactly the same thing. When both of them are 0, we get 0. So this is OR gate. Truth table. Truth table for this, I have A, B, and X. This is all the permutation should come here. I have 2 options for A, 2 options for B. In total, I have 4 options, 4-layer permutation. 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, 0. Then at least one of them. At least one of them. At least one of them. This is called OR gate. And it is very important. How to show that? What is the notation for OR gate? Let me write here. X equal, I want to show A or B, or A or better one, A or B. These are the notations that we use for A or B. Guys, we can have more than one input to all of them. For example, I can have input for AND with 3 inputs, A, B, C, and that can be the X output. When we have 3 inputs, then we can have 8 rows. Why 8 rows? Why 8 rows? Because each of them can be 0 or 1, 0 or 1, 0 or 1. So 2 options for this, 2 options for that, 2 options, 2 times 2 times 2 is 8, for example. All of them are 0. When only A is 0. When another permutation, let me write all of them for you. When these 2 are 0, when 2 of them are 0, 1, sorry. When 2 of them, 1, 2, 3, 4, 5, 6, when all of them are 1, 1, 2, 3. How do I have all the, and I have one more here. Let me actually delete this. Let me delete that. And you know what, let me erase this again and have a better table. Yes, I think it's better to delete this bit and make a better table to have all of them. Let me do that again. Delete this. I don't know why I cannot delete that one, and delete this as well. So, okay, I have 8. I should have 8 rows, A, B, and C. And here I have X. As I said, we need to have all the permutation, all zeros. When one of them is 1 only, when only, look, one of them in these 3 rows are 1, then 2 of them are 1. When 2 of them, and the last one, when all of them are 1. These are all the permutation that we can have. This is an AND gate. All of them should be 1 to get 1. All of them should be 1 to get 1. Only the situation that we get 1 is this, when all the inputs are 1. The rest, because we have 0 in that, all the rest would be 0. Let me do the same thing for the OR gate. If I have another column for this, I call it Y. What is Y? I have A, B, C, but I have OR gate. A, B, C. Here is Y. The output, I call it Y. this one is 1, the output is 1, when at least one of them is 1. So as you see here, all of them are 0, we get 0. Here I have 1, 1. Here I have 1, 1. As you see, in all other rows, I have 1, at least 1, 1. So this is the difference between AND gate and OR gate. So guys, what we can do, we can actually mix these gates together. For example, if I have one OR gate here, I have input A and B, and I have another AND gate in front of the next input, which is C. You can actually write all the permutation of them. So for example, let's do another truth table for this. This is A, this is B, this is C. So what happens? And here is X. Look guys, all of them can be 0. One of them can be 1. All the permutation. This is the truth table. For the truth table, we've got to write all the permutations. So look guys, A, B, C. In the first situation, let's do it together. A and B is 0. This is A, B, C 0. So this is OR gate. When this is 0, this is 0, this is an OR gate. When both of them are 0, definitely this is OR gate. At least one of them should be 1. So when both of them 0, the output of that is 0. When this is 0, when this is 0, this is 0, definitely that's 0. And when C is 0, the both input for this AND gate is 0, the output is 0. Now, if AND is 1, if A is 1, if A is 1, that becomes 1, but because C is 0 in AND gate, again, all of them should be 1 to get 1, the output is 1. But this is 1, this is 0, we get 0. So when C is 0, I don't care about others. When C is 0, because both legs should be 1 to get 1, in all these rows, when C is 0, we get 0. What about here? This row, A is 0, B is 0, C is 1. So A is 0, let me use green. This is 0, this is 0. So 0, 0, OR gate, I get 0. And C is 1. And when I have 0 and 1, again, as an AND gate, I will get 0. So this will be 0. Let's go for, let me erase these ones and another row of this. So let's go for this one, this row. A is 1, B is 0, C is 1. That's an OR gate. When one of them is 0, 1, we get 1. There you go. So I have 1, 1 here, 1, 1 here. AND gate, when both of them are 1, I get 1. There you go. This is 1. These two situations is exactly the same. One of them is 1. So in that case, this is 0, this is 1. The same thing happens. 1. When all of them are 1, again, same thing happens because the OR gate is 1. So as you see, for any combination, we can have this truth table and we can analyze what happens as an output of this SIG. So this is the first video for this week. We have 2 more videos. Please watch them and do all the exercises. Thank you.